Looks good. Settings. There's a way to turn this off. I forgot. I guess you won't see it anyway. Okay. Sorry. Hold on. It's Control Alt H. Did that work? No. Still there?
No, no, it's not that I can.
No, it's not. Yeah. Give me a second. There's a way to do this. Just been a little while.
I guess you can leave it.
There's a way. There's a way. Oh. Hide self view. Hide show me on the small screen. There is a way. I thought it was Control Alt H, but sorry, I would have prepared if I'd known. I'm so sorry. Okay, let me see.
Do you need to click this one?
No. That's not the issue. The issue is it's actually usually under more, but it's I don't think it's on your system. I'm sorry.
Don't worry.
Okay.
We can live with it.
It's not yet.
Maybe it disappear by itself.
Well, it's not. It's not an option on yours for whatever reason. Okay. Anyway. Okay.
All right, everyone. Welcome back to another seminar. It's a pleasure to introduce Lincoln Carr from the Colorado School of Mines. Lincoln has become a very good friend of Northeastern University. Every time he comes to Boston, he comes and visit, and he tells us about his latest great ideas. And so Lincoln is the ultimate Renaissance man, I say, because he's working on so many interesting topics that are hard to list. But you can tell by his multiple affiliations already. So today he's going to tell us about his latest work on fractional multiscale mini-body quantum materials, phase transitions, and causality.
Sounds good. And I think I finally figured out how to do all this.
Yeah.
And we still have this one, but hide floating meeting controls. It was Control Shift H. Okay, fantastic. We have solved the problem temporarily. Okay, except that this no longer talks to the device at all for unknown reasons. Okay. And I have no control. I'm so sorry. Give me a minute. The entire thing is frozen. Okay. Sorry, guys. We'll try again. I think PowerPoint just crashed. So, beginning, try this again. Here we go. And then I'll try to share on Zoom. Okay. I think we're good. Maybe. All right. Amazing. And this doesn't do anything. All right. I'm not going to worry about it. I'll just come over and press buttons. Hi. Sorry about the technical difficulties. And I'm very pleased to be here today at Northeastern. I have been collaborating with one of your faculty since we were both postdocs, Professor Min-Chong Wu, who's a fantastic physicist, a great colleague and friend. And I've known Greg for many years. I think I first met you long ago when you were at UT Austin. And of course, Adrian, I've known through his work and then personally visiting here. And it's really an honor to be here. So thank you very much. I'm going to talk today about something that seems super mathy and is in fact incredibly practical. I want to emphasize when I talk about fractional multiscale, I'm going to get into fractional derivatives. I'm going to explain what they are, but I don't want you to feel they're too exotic. So if I have this bottle of water, so I'm from Colorado School of Mines, so I have to talk about rocks. It's required for all mines faculty. So I have this bottle of water. I go out to the lawn there and I pour the water in, and it goes through, the rocky soil. And if I try to measure, how far this water propagates into the soil as a function of time, I'm going to find it's not Brownian motion. It's not normal diffusion. It's going to go faster than that. Okay, it's going to go further. And that's because there's the interstices that give it rapid propagation. And so those are called levy flights, and that's really going to be what this talk is about incorporating that into the many-body problem. So lest you think it's incredibly exotic, with this water bottle, I can go demonstrate this effect on the lawn. Okay, so just so you know. So it's actually very normal in soft condensed matter physics. A lot of what we're doing in quantum information now and hard condensed matter physics, we're taking soft condensed matter ideas and we're really pulling them in. You were just telling me about kind of glassy physics, for example, Greg. And this is another example of something that's incredibly common in classical and biological systems. And now we're going to bring it into hard condensed matter and quantum information systems. That's the basic idea of this talk. Okay. So now really specifically, let's get into what these fractional multiscale mini-body quantum materials are. And I'm going to talk about three topics. I'll tell you about them right now. Of course, once again, and now it is not letting me change slides. Oh boy, let's try the mouse. Okay. It freezes out and will not let me change slides once I display on Zoom. I can try to change the display method, but it seems that it's going to have this problem regularly. Yeah, I'm so sorry. It is frustrating, but that's life. Okay, so I'm actually even locked out. Hold on a second. If necessary, we can just go to the board and forget about this, and I'll tell people on Zoom what's going on. Okay, so let's end the slideshow from beginning. Yeah, it's really seems that it really can't handle both things at the same time. Okay, we will try one more time, although I have my doubts. So I did screen one before. Let's try screen two. That's the only thing I think that's any different. And then, okay. All right, so no. And I get onto the other screen, and then it's possible that it will allow me to advance slides here with next, although it would be quite a pain to do this every time. Okay, now it's going. We'll see what happens. Okay, so I'll give you a little bit of an introduction to what fractional calculus is and why it matters in real physical systems. And then what I'm going to do is walk us through single particle quantum mechanics to the problems that you know from undergraduate quantum and see what happens. They're actually very interesting. Fractional derivatives introduce a kind of non-locality into the problems. You have to resolve those problems. And then I'll talk about phase transitions, basically Monte Carlo solutions in classical and quantum systems. And then finally, I'll talk about my latest work on dynamics using MPO methods, which of course Adrian knows very well. And that's sort of hot off the press. I haven't even submitted it yet. So this will be the first place that's ever heard about that work. So, okay. So first of all, fractional calculus has a very long history. Starts in the 17th century. L'Hopital writes to Leibniz and says, hey, is there a square root of a derivative? And what would that mean? And mathematicians spent a long time trying to resolve this. Euler got into it through gamma functions, and you'll see those do play a role. Liouville and Riemann got into it. It got into mathematical physics, as a way to interpolate between these integer order operators. And then finally, Caputo wrote down this derivative that really allowed engineers to use it. And that's where everything sort of took off, like the groundwater example I gave, that's really due to Caputo. So then there were applications in a lot of classical things like anomalous diffusion and control theory. In the early 2000s, this guy working in France, Nick Laskin, sort of asked what would happen if I solved this problem in a quantum mechanical context, and he started to write down some solutions. And that's kind of the beginning of what we call fractional quantum mechanics. And then my group has been working in this area since 2017. And we've gone through, everything from integrability in nonlinear dynamics all the way to, these quantum many-body things you're going to see now. So it takes a while to get into, but I think it's well worth it. What do we mean by fractional calculus? So of course, you would call the usual derivative, the nth order derivative, where n is an order of z as element of z. Okay, so now we just say, well, what do we mean if n is non-integer? And the simplest thing that we mean by that is just if we were to compose multiple operations, we would recover the integer derivative. So this was kind of what L'Hopital was asking about originally. So just mathematically, that's a simple idea of what it would be. So if I have a function here, if I do a square root derivative, another square root derivative, it should equal to total to a full integer ordered partial derivative. Simple idea. Okay. So as physicists, we might say, well, that's great, but how do I use that? Right? And so how we use it is through what's called the Reed's fractional derivative. So that's not the one that Caputo wrote down, but it is the one that's most useful to physicists. And what you'll notice here is that this, spatial derivative to the qth order, right, looks like multiplication by minus k to the q. And so in that sense, you can understand it through, through the Fourier transform. And that's how most physicists will think about this. I'm going to do this one, and I'll do what's called Grunwald-Lednikov derivative later, which is a discretization of this idea. Okay, any questions so far on the math or the notation?
How q equal to 1? If q equal to 1, we just have minus pair.
Right, and so usually these definitions do not limit very well to integer cases.
Oh, okay.
Yeah, and so you have to take very good care in this limit. And that's one of the problems with derivatives, with definitions of fractional derivatives, is they don't have nice mathematical properties across the entire range of Q. So, and all this I'm sweeping under the rug, but throughout this work, we're very careful to do that limiting process properly, and for the integer order to reproduce the integer order results with the right kind of expression. Yeah, great question. Yeah, of course you don't see the I, right? So it seems strange, right? Okay. So, all right. So the basic physical thing that creates these fractional derivatives, just as I described with the water and the interstices in soil, is what's called levy flights, right? So levy flights is a general description of stochastic processes. They're scale invariant. So now Brownian motion is the one you're used to, and that's actually a special case. But in general, you get what are called heavy tail distribution. That's an example of a levy flight. You notice that this particle is kind of wandering around, and then bam, it moves a long ways, and then it wanders around, and bam, it moves a long ways. So somehow, something else is happening to this particle. The case that you're used to, right, is that the average of x squared, the variance, should go like this: diffusion constant times t to the 2 over q, right? And so if q is equal to 2, the usual second order, then of course this is t. Okay. But in general, this is tunable, and that gives rise to these heavy tail distributions. So now what does that look like? It comes out of this, what's called characteristic equation, and it's the Fourier transform of the PDF, right, for the jump lengths, right? So, if you do this on a linear plot, you can see that you can tune pretty continuously between these different q's, and q equals 2 is kind of this red one, the usual sort of Gaussian, and there are other things that, make it narrower or broader. And if you put it on a log scale, you can really see the difference, right? Here's that Gaussian case, and here are these heavy tails. And now maybe why it's very hard continuously and analytically to connect those two kinds of functions. Okay, and that's the issue. And so, those tails really change a lot of things, and they're going to change a lot in quantum. In quantum, we're always thinking about tails into a barrier. So you can imagine that those tails will change a lot of the story in semi-classical physics and tunneling and other things. Okay, and the actual characteristic, the PDF, you can see it goes like e to the minus lambda k to the q. So you're probably used to, k squared, but now it's just going to be k to the q. So, very simple generalization away from the Gaussian. Okay. So now the other concept that we need to understand the effect in phase transitions is the Hausdorff dimension. So how many people here have heard of Hausdorff dimension before? There's only a few of us. So just say you've heard of 1.5. Okay. So Hausdorff dimension is a little bit like, levy flights. It's kind of talking about the way that we fill the space. So it describes how fully a path or any set fills the space. You're used to integer dimension, 1, 2, 3. A Hausdorff dimension is the limit as, if I have any object, I put little disks to cover the object. And as I make the disks smaller, right, it's the limit of how many I need with how fast it gets smaller. So it's what's called a scaling dimension, right? And what Hausdorff dimension is, it'll pick up on things that will do is it'll pick up on things that are bumpy or jagged. So for example, this Sierpinski triangle, which comes out of a cellular automata, one of my favorite subjects I work on is dimension 1.585, right? It's neither one nor two-dimensional, right? And fractals are one example of this, but it's not only fractals, just basically anything bumpy, you can get this kind of effect. Okay. So, right, so Brownian motion has a Hausdorff dimension of 2. It gives you, complete filling of the space, right? Ballistic motion, no scattering at all. The particle just keeps going. And so you can think of Levy flights as interpolating between those. You have some ballistic trajectories that then are arrested by some locally Brownian, then another ballistic trajectory. That's very easy to set up in physics, and I'll show you some examples in a minute. So that's the kind of thing that's going on. Again, it's super common in classical and biological systems. We just don't often think about it in physical context. So Levy flights in physics, physical examples are motions of particles undergoing certain kinds of turbulence, foraging and search patterns in an animal. The animal's eating here, runs out of food, walking a long ways, finds another patch of grass, eats over here. You can imagine it's exactly a levy flight, like what cows do is a levy flight, right? Patterns of signals in primate brains, you look in EEG, for example, for signals like that. Financial markets pretty famously are, person making money over here, they run out of ability to make money, now suddenly the market shifts. Those shifts are these in-between ballistic flights. And optical systems. Okay, and so for financial markets, here's a specific scaling behavior in the dynamics of an economic index, and you can see these very kind of heavy-tailed distributions. And I believe, let me see, I even made a note about what the actual Hausdorff dimension of this thing was, but I think I can't. I'm sorry, I think I can't get to it because I can get to it on the screen. Great. Okay, so that was that's an S&P 500 over 6 years and a fractional order of 1.40. Okay, so you can literally do a fit. And then the optical example is if you have beads of different sizes and you look at scattering between those beads, you exactly can get a Levy flight. And the important thing is the distribution of beads follow that PDF that I showed you earlier. So that's a little bit of the physics that's out there. People have really made these systems back in 2008. People just haven't done, like really many body problems. They've only done sort of single particle problems here. Or simple wave theory here. You have a question, Ming-Sean?
Yeah, people are saying financial markets are chaotic. So what will be the chaotic response?
Well,
what's the correlation with this?
Well, okay, so chaos is complicated. So it depends on what kind of chaos. So now, if by chaos, we mean stochastic, keep in mind that there can be a strange attractor. And so you and I know this from our work together. I think I'm telling you things Remember, there's a dimension of the strange attractor. And so once you get on the strange attractor, now you're exploring, right, this lower dimensional space, and the exploration of that space does not look stochastic or space filling, right? So strange attractor is typically a fractional dimension. Exploration of the strange attractor will look like a Levy flight, for example. A lot of people think chaos means stochastic, and I mean, this gets back to fundamentals of thermodynamics, and so maybe we could debate this at the end. Actually, maybe Greg and I can have a debate about this. But I think it's a real good question when we teach stat mech exactly what we mean by the kind of chaos that thermalizes versus the kind of chaos that you see in a system like this.
Or you just think what deterministic. Okay. So they are described by the differential equation, the integral, not fractional differential equation, right?
Well, again, if we think about a system like this, these balls are excluded regions where you cannot get to, right? And so anytime you have a system where there are excluded regions, and the excluded regions have a PDF that has power law tail, then you're going to get this Levy flight effect. So many natural systems look like that. I'm sorry, I'm not sure which literature on finance you're referring to. We can maybe come back to it at the end, and we could talk about that. But pretty famously, if you look, for example, at the probability of a stock market fluctuation, versus like how often that fluctuation occurs, it's an inverse cube. I mean, definitely power law. So power laws are all over, finance. And I think that's because finance has many scales operating, and it has a time dynamics like this. And the combination of those factors leads to, a complexity description rather than a simple statistical description. But I would argue it is the generic statistical description for complex phenomena. Okay, and this is a baby version of this, just simple multiscale stuff. Okay. All right. So, so what's the source of fractional derivatives? Well, you know, in the diffusion equation, it's originally derived as a result of many particles undergoing Brownian motion, right? So you think of an ensemble of particles now undergoing Levy flights. This modification will give rise to this fractional diffusion equation like I described. So, and then Levy flights derives the second derivative, you know, in the diffusion equation to become fractional. So how does it work in quantum mechanics? Well, you start with the Schrodinger equation. The Schrodinger equation can be derived, I remind you, as a Feynman path integral over Brownian motion paths. Okay. So if you replace those, you know, Brownian motion paths with Levy flights, you know, sort of automatically, right, you know, you get a fractional Schrodinger equation. Okay. And so you need some kind of underlying potential that will drive those Levy flights. And I actually have an experiment I'm working on now in thin films in magnetism, actually to you know, make this work and find these critical exponents I'm going to talk about. But I can't present that yet because it's still like totally in progress. So this is going to be the theory today. Okay, so before I go on, any questions about this? Because now I'm going to dive right into the Schrodinger equation. So was that enough of an intro to get a flavor? Have I convinced you that it's not just a math problem between L'Hopital and Leibniz, but practical? Yeah. Okay, good. One person gave me a thumbs up, so I convinced one person. That's all that matters. All right. So only one person believes. All right, so let's talk about the single body effects. This is still more sort of the warm up, and I just want to give you a sense of what it would do, the Schrodinger equation. So, you know, here's the usual Schrodinger equation, you know, scale weight H bar and n, which truly shows up in theories. And then you use your usual Schrodinger equation, you now have a fractional derivative, and then, you know, you can define it through the Fourier transform. And if you use this and then you do some, you know, finite differencing, you know, you can write up a numerical method. And now I'd like to highlight my collaborator and student, Josh Lewis, I should have mentioned on the very first slide, who very much developed an excellent numerical method that converges to arbitrary accuracy. No one has ever done this for Schrodinger equation, and it is far better and faster than all the anomalous diffusion codes out there. The guy is very good. We were talking about good students over lunch. So that was the first thing he did while he was a master's student. And I told him, take 2 more classes and get a PhD, please, because this is already far too good for a master's. Like, nobody solved this problem, and there's a ton of geophysicists doing it. And why is it a hard problem? Because of boundary conditions. Because fractional derivatives give you effective long-range effects, and then you have to really be careful about the boundary conditions in your numerical implementation, or you make errors, and the errors are severe. So most of these codes converge to a few digits. His are arbitrary accuracy. So I'm not giving you the details because of time, but it's really quite remarkable work. Now, there is an exact solution to the fractional Schrodinger equation with 0 potential. And that's this Mitai-Leffler function, and you see it's got a gamma function in it. I told you earlier that Euler was fooling around with gamma functions and fractional calculus. So we knew early on they were connected. So if you generalize, you do the sum of this power law over this gamma function, then you get this exact solution. And there's even a parameterized version of this. So this is in the table of special functions. And if I plot this thing on a linear scale, you can see that as I move away from integer values, the tails start to do something weird, and the middle looks pretty similar. So you can guess already that the exact solutions are going to do something strange in the tails. Let me show that to you on a log plot. Okay. This is the integer case, right? This is the non-integer case. And it can even develop really quite a lot of structure. Okay, so, the exact solutions to the fractional Schrodinger equation can be derived. They're going to have strange tails, and that will matter whenever we're going into a barrier. So that's where we're going. So I'm just going to pause. I happen to love this kind of stuff. If you saw my applied math affiliation, not everyone does, but is this helpful to know? This is like the generalization of the exponential. So, you have an exponential that solves the Schrodinger equation going into a barrier. This is the same thing for fractional case. Okay. So the first thing you do, you solve particle in a ring. So you go solve that and you find out, oh, well, I solved this under periodic boundary conditions. I told you boundary conditions are non-trivial in these problems, but guess what? It's the same energy, but now you just have a cubed power. Same solution as you're used to. In fact, the actual wave function, it's the only solution I know of for fractional Schrodinger where the wave function is exactly the same. One of the shifts is the actual energies. Okay. And so if we think about, the particle on a ring, and we're now able to evaluate this code. I told you this code was awesome. And now since we have an exact solution, a numerical solution, I can show you that, the pointwise error in this code over the entire domain of the solution is, less than 10 to the minus 14 at everything, which is pretty remarkable, given that other people previously were like 10 to the minus 3. Okay. So that was maybe for Adrian, just to, tell you I'm still into numerics. Okay. Great. All right. So now let's do something more interesting. We'll do the harmonic oscillator. So now, Of course, at very long range, we have an idea that we're going to return to those kind of strange heavy-tailed distributions. So here are the actual solutions, and you can see that it's the ground state of the harmonic oscillator solving this problem numerically now. And you notice, it doesn't deviate that much, right, to the eye. But now let's look at it in a log plot. Bam. Okay, and this is just the noise floor, by the way, in the code. So here's the usual harmonic oscillator solution on the log plot, the polynomial, and then here are these crazy long tails. And so it gives you a lot of additional tunability in the problem. You can kind of zoom in on the tail and see what's going on. And then very interestingly, the even spacing that you have in the harmonic oscillator, you can now tune. So this is the value of the fractional order from 1.7 to 2.3, with 2 being the usual, and you see how the green is linear, as you expect for harmonic oscillators. It allows you a kind of way of making your spacing nonlinear, which I remind you is what you also need for for qubits and Josephson junctions, right? So we know Josephson junctions, you put the extra periodic potential on the harmonic potential, and that allows these things to be not quite linear. So here's something you can do about addressability in harmonic systems. I'm just going to walk through the solutions real quick. Here's the finite well. I'm sure you can imagine the finite well. A similar thing will happen, right? We'll have, here's orders of 1.82 and 2 and 2.2. They look pretty similar, but then when you look at the tails, the tails are completely different, right? So you can penetrate way into the barrier. You might think this really doesn't matter, but actually it matters for bound states, right? And so I can either have less or more bound states. Here's two right here. So those are the bound states. So I can have, sorry, here. Yeah. So I can have less or more bound states depending on what I do with the fractional order while keeping the well of same depth. Okay. So finishing up this story, just one more slide on this kind of intro. This is a paper that's actually just was published in JPhys A few days ago. This kind of mathy paper is now we solve the double well. The double well, I remind you, is the paradigm for a Josephson junction. So it is really the beginning of the building of qubits, is to think about the double well. And so, here's a double well, and I did a, what is this called? Doubling potential, right? Quartic quadratic. And then I went ahead and solved this. Here's the ground state and first excited state, as you see solutions. And to remind you, the states can be localized in the left or the right by taking the symmetric and anti-symmetric superposition of those states. And then you can determine the tunneling between wells according to this splitting. It looks like pi over E1 minus E naught, right? And so there's a frequency of tunneling that's related to this energy difference, which is exponentially small. And that's why, it's very hard to build cat states and things in double wells. So, so amazingly, not only can you tune the tunneling enormously, but you can even flip the symmetric and the anti-symmetric states to ground state. So, so I think that's pretty cool. So, here's the way that you can tune your tunneling time, and you can maybe think about getting more cat-like states. And honestly, we didn't solve the many-body version of this problem. If anybody wants to solve it, it's pretty straightforward. So if there's already a problem anybody in this room could do, you go and you do the noon state problem, but you do it now with the fraction dispersion and resolve it. Okay. All right. So that's the end of my single particle quantum. We've just revisited an entire undergraduate quantum course and resolved all the problems. Does anyone have any questions before I go on to the fun stuff, which is the many body? No, straightforward enough. Okay.
I guess maybe a question here. So, suppose that I wanted to try to apply this to some qubit system.
Yeah.
Do I have control over Q? Like which fractional derivative should appear?
So so up until this work, and the one optical experiment, I don't know of anybody who's actually built fractional derivatives from scratch by building the right kind of Levy flight. I know how to do that in a lattice. I didn't publish it yet. Right now in the experiment, I'm doing it in a superconducting system. Okay. And that's because, superconducting wave function is big. It's very big. And I need a distribution over lots of sizes that are much bigger than the, 1 angstrom or whatever, a few angstroms. And so I need something that will sample over lots of sizes for that to work. So, I think it's good when you're talking about something that's sort of larger scale. You can think of a fraction derivative as something that averages over a bumpy material by catching lots of scales at once, and it gives you an overall way that it'll propagate. So whatever your wave function is, it's got to be bigger than the scale of bumpiness. So if you can do that, then yes, I can tell you how to design them. Mingjong and I had a grant to do that together, and we're still talking about that. And I'm now doing it in superconductors, and maybe we'll come back and do it in big films or other your programmable systems you have now. But it's not that Anderson localization. You can't do Anderson localization on 10 sites. You need 50 or 100 because the localization length is too big, right? And so similarly here, you need some number of sites in each direction to be able to do anything. It's more like Moray also, right? Yeah. Is that helpful? Okay. Great question. All right, so now let's talk about phase transitions in fractional quantum many-body systems. We'll see if we get to dynamics. I see I'm already a little ways in because of the lost time with the tech early on. All right, so if I want to write down a classical fractional Ising model, I mean, I'm sure you can imagine, it's really no different. Now I have to suppose that my interactions are driven by exchange particles that undergo Levy folds, right? And there's no reason that you have to do an Ising model. I'm just choosing to do that, right? But if you can do it in any many-body model, but we'll start with Ising. And so then you obtain an Ising model with interaction strength mediated by total scalar J naught and a biasing field with strength H. And then let me show you maybe what the quantum version of that looks like, which might be useful for the quantum folks in the room. So from Landau-Ginzburg equation, we can derive a discrete model with a set of spin-1/2 qubits. It's got to have a translationally invariant J of R. So that's this long-range mediated interaction. If it was a Hubbard model or something, it'd be long-range hopping. Okay. There'll be an overall interaction strength J naught, transverse field strength G, and biasing field strength H. And then, here's the model. So it looks like your usual Ising model. And maybe you guys know that like for spin glasses and whatnot, there's a Ji out front here, and that's random. So this is, it's neither nearest neighbor or simply ordered, nor is it random like a spin glass. So in that sense, I like to say these models interpolate between order and disorder. That's my personal way of talking about it. And then, here's the usual, transverse and longitudinal fields. And note that R is J minus I here. So it's the difference. So translational invariant. And now you're like, okay, what is that function J of R? So I'm going to show you that function. Okay. So here it is. So if you take that fractional derivative, that Reed's derivative that I showed you, and you discretize it through finite differencing, it's called the Grunwald-Letnikov derivative. That's another way you can define a derivative. And when you do that, you're gonna find out that the derivative looks like, in principle, an infinite sum over all possible finite differences with this choose out front. Okay, so that's like a very well-known result. And if you then, take that into this exchange process, then you find out that what you need is you need Q choose Q over 2 plus R, with this alternating sign out front. Okay, so yeah, that's your generalized exchange. And again, you might say, well, that seems super mathematical, but I did just tell you that you can build just by having excluded regions and pass between those regions, and you get it automatically. Okay, and I have shown that separately in simulations I won't show you. Okay, and now I want to give you a sense of this crazy looking, modulator of the exchange, right? So that exchange matrix, this Gij, it's often random, like I said. This is a kind of a funny one. Now in the position domain, you can expand this J of R. You guys can all do this analytically, and you're going to get a dominant power law, at very large scale, and then you get it, an infinite series, and here's your first correction in the series. So at small and medium scales, you get very non-trivial deviations from power law behavior, but at long scales, you get power law, which is great because we know a lot about power law terms in Hamiltonians like this. Now I'm just going to show you a plot of what this is like. So here would be, say, 1 over R squared power law, and you can see that, at very long scales, for example, I think it should be -1 plus Q, so it should be 1. Okay, so the orange one should be approaching the same slope as that red one. I've arbitrarily shifted that up. Do you guys see that? Yeah. But at very short scales, it's deviating a lot, right? And you can try to pull out sort of the next scale, and then you'll see even then you deviate. So anytime you're in shorter range, it starts to really deviate. So keep in mind, long range power law, short range. If Q is greater than 2, which I didn't show here, it actually also flips sign, so you can get some antiferromagnetic contributions. And then you get possibility of a kind of frustration going on in the problem. Okay, the other way you can look at this is just through the band structure. So let's just do the momentum version of the plot I just showed you. So in the momentum domain, I kind of already showed you this when I solved the single particle Schrodinger equation. But you notice that you have your usual solution, but now it's to the Q power. Right, so that's your usual band, but it's going to be sort of squished by Q, and now I'll show you a picture of it. Okay, and so Q equals 2 is this red one, that's your usual band. And then as you make Q smaller, you're kind of squeezing down the, the band edges, right? And so I would say, there's a road here that, this fundamentally alters the symmetries of critical behavior because critical behavior cares about the large wavelength limit. And that'll be, fundamental to critical fluctuations. So we can already guess that our critical exponents are going to be modified by this. Okay, I hope that gives you some intuition. People think about these things differently, but here we have position, momentum space I've given you. And then I tried to connect it also to Levy flights. Okay, so I'm going to go on and show you a bunch of results on critical exponents. So let me just pause here and see if you have an idea of like what is the model I'm solving and where it comes from and why it matters.
I guess the question similar to before. I mean, do you have a system where you can control J of R, its functional dependence on R?
Yes.
In other words, choose the Q.
Yes. Right, and it's the solid state analog of that optical system I showed you. So what I do with this is with I don't know if you've seen this, we put in a proposal at some point together, a condensed matter experimentalist at Mines, and so so we have superconducting material where we put in random scattering centers throughout. And then we put in excluded zones through etching, and those excluded zones we put in. We do that on a PDF that has these power law tails, and that exactly produces pathways for the superconducting wave function that will follow these Levy flights. So yeah, that's one way to do it. Another way to do it is to actually,
and the signature is going to be in critical exponents.
We think so. We think so.
Okay.
Yeah, I mean, we're in the middle of the experiment, so I don't want to say the results yet.
That's the way you plan to like extract that there are these fractional sort of derivatives present.
Well, we're thinking about different signatures around phase transitions, and I think my colleagues have asked me not to say more about it because they're extremely excited with some preliminary results, but I wasn't permitted to present that yet today. But samples are made, are measured, and we have results, but we're debating them right now, and they are around, yes, critical exponents and phase transitions, yes. Okay, and superconductors again because the wave function is big, so that's the idea.
Meaning the Cooper wave function.
Cooper wave function, correct, that's what I mean, yes. So, okay. Let's see. And then if you wanted to program that into an optical lattice in, say, an EC experiment or something, or any just, artificial lattice system, even in 1D, you would need to use some number of Fourier components. And the typical number you need to see emergent fraction behavior is about 5 to 10. So you can think of it as a multiscale lattice. One way I like to think of these things, derail the whole talk, but I'll just make this comment really quick. When we like to think about these things, you're used to seeing and then if V of X equals V of X plus A, right, this thing is about equal to minus H bar squared over 2M star del squared. That is to say you get rid of the potential. Okay. And so you notice that the only thing that's affected is the constant. Let's make this 1D. Sorry. It's really simple. Okay. And so if instead V of X is equal to a multiscale potential with a number of wave numbers in the problem in the right proportion, then this guy is going to be replaced by minus H bar squared over 2. There will be a CQ, which will be related to this effective mass, but it's a modified version to deal with units primarily, and then partial to the Q, partial X to the Q. In other words, you modify not only the constant, but also the derivative, but again, get rid of the potential. So that's one way you can do this. That's a practical way. Okay. More questions? All right. So critical exponents. So now with finite size scaling theory, we're going to obtain the 6 universal critical exponents, which I'm sure you guys know from classes. I want to again boast about Josh. He wrote his own Swenson-Wang or cluster Monte Carlo for long range problems, and he got 100 times faster than anyone has had in the literature that we can find anywhere. I mean, he has a lot of speed ups. It's very impressive. And that's one of the things that was actually essential to this work. So just to remind you, here are these 6 critical exponents. This anomalous dimension will be especially important. And you extract them from various measurements like the magnetization, the susceptibility, the specific heat, the binder's cumulant, and the connected spin-spin correlation. So this is kind of all textbook stuff, right? and then you do finite size scaling on that, and that's how you obtain these critical exponents. So I'm not going to really go through that process because I think it's well known to some people in the audience, but I have some backup slides if you're not familiar with that, and then I'll be happy to explain it to you in detail. I do want to remind you, I actually didn't know this until I got into this work. Do you guys know this relation? This is so interesting. I didn't know this. This is a well-established thing in critical exponents. There's a geometric interpretation of scaling near a phase transition, right? Where the anomalous dimension is telling you something about the fractional dimension of these correlators at very long, large scales. And so it's actually dual to the Hausdorff dimension, which is why I told you guys about Hausdorff dimension before. And if you think about how critical phenomena work, that they're kind of self-similar at any scales, then you can guess Hausdorff dimension might be involved. So this is an established and derived result that eta plus dh is equal to 2. Okay. All right. So now here are the results of Josh's awesome code, which I have really pushed through the ringer. I feel very confident in these results. And this is going to be the classical case. And we're just going to do 1D for now. So for the 1D classical case, now normally phase transitions aren't allowed in 1D, to remind you, right? There's this wonderful theorem that tells you shouldn't have them, but that's actually for short range interactions. So by thinking about the bounding power law, we know at what point phase transition should be allowed. And here's all the critical exponents. I know that's a lot at once. I'm not going to dive into them in a couple of slides. Okay. By the way, I'm only 33 minutes in. There was actually that much technical difficulties at the beginning. So you let me know when you want me to stop, but at least I'll go through this part and I can maybe do a moment of dynamics. So first of all, let's talk about the classical isotherm delta and the correlation length nu, right? So you've got a KT behavior as you approach Q equals 0 and Q equals 1. So there's nice KT boundaries on the edge of the existence of these phase transition, right? And then I think that you might be interested in some details of these, but I think I want to tell you a little bit, actually, given the time, about the anomalous dimension. So the anomalous dimension is this red one, and then this dashed line is I'm actually going to plot a particular function that's behind it. I'll tell you about it in a minute. Okay. So now I told you that the correlation function in the derivation of eta plus dh equals 2, they derive it by saying that correlation function you interpret in its dual representation is an exchange particle path probability amplitude. Isn't that great? Because we know that if we now put in Levy paths, that should modify this, right? So even by going through this original derivation, Josh figured out that, hey, maybe dh is related to q. And so we put out this hypothesis, which is this red line, that maybe eta is equal to 2 minus q. We can just use that to predict eta. Okay. We did find that. It allows them to precisely tune the Hausdorff dimension of the critical fluctuations. We've got chi-squared assigned to this result. And then you can understand the impact on critical exponents because you're tuning the anomalous dimension through this dual relation. So I thought you guys might find that interesting. Okay. And any questions about that? I mean, I'm super proud of this, actually, because we had no explanation at first for the crazy things that we got out of this code.
So you define the beta as non-convention, right?
Eta, sorry? Beta. I'll tell you about beta in a minute. Yeah, that'll be the next slide. Right now, I'm just talking about the anomalous dimension, which is this red one, eta. Yeah. So next slide will be on that exactly, right? So for specific heat, magnetization, susceptibility, things that you're typically measuring more directly in an experiment. Okay, so this is our interpretation. Is that for Q, you see for Q less than a half, you get very different things than for Q greater than a half, right? And so our interpretation here is that the fact that alpha, gamma, and beta, freeze to 0 or their mean field values for small q is saying that large-scale spin coherence is not driven by fluctuations in energy. That's the idea that we have. Okay. So why is this discrepancy between these different constants compared to? Just to remind you, I had something that varied, throughout Q, right? And so something I didn't understand about critical exponents, despite having taught it many times, is that some are picking up on more sort of local effects and some are picking up more on global effects, right? So for Q less than half, the interactions are effectively short range. And so these exponents are insensitive. Okay. So this concept of global versus local sensitivity of critical fluctuations, because I had never really thought about this in the context of these power laws, I was always doing nearest neighbor models. I didn't really understand this point. And so you can really see this global versus local sensitivity with these derivatives. Okay. All right. So below a half, it's a weaker marginal parameter. It's affecting only those global exponents I showed you before. Greater than a half, it's a much stronger marginal parameter. It's going to affect all of the exponents. Okay. Anyway, that's our interpretation. This is now under review at PRL. We'll see what the PRL referees say. Perhaps some of them are sitting in this room. I'm looking at Greg. Okay. Okay. Greg's like, I already reviewed this thing. Oh my God. All right.
Just quick question about
Yeah.
how you obtain this data point. So you have to find first the critical point for the phase transition, right? You're sitting
Correct.
at the
Correct.
critical point.
Yeah.
And then you have to do a
Finite size scaling.
daily collapse of the.
That's right.
formation of-
That's right.
Okay.
And I have this all on my backup slides. I was just worried about time, so I moved them out. But can you ask me then, and I will pull you up a bunch of plots so you can see exactly how I did it.
Okay.
And feel free to suggest modifications. I mean, one thing I had him do at first was to use this, old cluster Monte Carlo modified for long range to reproduce all the known power law stuff, which I had actually done a lot of before, and he did that perfectly. So I'm pretty confident in the code. And then we have this nice interpretation, including this almost perfect fit to this line. I mean, so I think I feel comfortable with the calculations, but it's tough. It's a new area. I would love someone else to try this as well. Okay, and then just to remind you, I can map the D+1 dimensional classical phase transition onto the 0 temperature quantum phase transition in 1D, and because it's D+1, and with these long range breaking the phase transition theorems, I can go to P = 2 instead of 1, right? And then here's the whole study. You'll notice some things are pretty similar. Things are flat up to Q = 1. I've got a KT transition. There are a lot of things that look like the quantum problem. That look like the classical problem. Again, this is just me solving the 2D classical problem and using the quantum classical mapping. So one thing you might not know, you were just asking about critical temperature. In that quantum classical mapping, the critical temperature map on a critical field, it's actually very complicated once you have long range terms in the problem. I didn't know that until I got into this. So I'm used to the nearest neighbor case where the mapping is quite simple. It's not simple. Okay, so, all right. So, right. So there is still KT at 0. We don't have KT at 1, at 2, the other end. We don't know why. And so that's an open question. Okay. For the anomalous dimension, that relation that we talked about before, right? I think this was actually Josh's pretty interesting idea, but I think we can again say that below Q = 1, I've got this weaker marginal parameter like I talked about, and above Q = 1, it's, you're getting both local and global exponents being influenced. You'll notice that this thing starts to deviate from the this simple prediction on the Hausdorff dimension. And so we think this is the role of actual quantum fluctuations in that geometric relationship that I talked about. Okay. So I don't want to say more because of time, but anyway, that's how we think it's deviating a little bit. We think those are real results. They're pretty well converged. Okay. And then I'm just in my last couple of minutes, I notice I'm only 40 minutes into my talk, but because I lost some time at the beginning, can I just have I know it's 20 after now, but can I have a couple of minutes to talk about dynamics? Because I'm pretty excited about this. Okay.
Absolutely.
All right. So, so this is where I got more into things that I'm much more familiar with personally, because this is all at NPO, time event variational principle, kind of stuff. And Josh wrote his own code from scratch, which I thought was impressive. He just wanted to learn how to do it. And I had him reproduce known things. I'm comfortable with the code and his results. This is the same model that we did before. Ising model is my test case, with the same kind of direct interaction here, these kind of coupling terms. And then just to remind you, outside of a causal light cone, the correlation of any local perturbation should decay exponentially away, right? And Dij is just the metric. V is the velocity of what's called the Lieb-Robinson bound cone, which is kind of a causality bound for those that might not already know that in the room. Let's see, and C is this. So let's see. Sorry, I can't get into my notes. Okay, so I won't say more, but just to say that this is a well-known derived result for a bound on causality. So we're going to have to know something about the commutator between sigma IZ and sigma JZ at T, right? you can prove, there's a 2005 Carr paper that proves that commutation is related to what's called the bond entropy. The entropy, you know, cut the system in some link and you have some part over here and some over here, right? And you only measure this part. So that'll be quite key to how I do the light cones, which I actually didn't know no one's ever done before. So I guess I have a new way to identify light cones, crazily enough. So, okay, and so what are we after is what's called the dynamical critical exponents. To remind you that that relates, you know, correlations in time to correlations in space, right? And I'm going to have three ways that will all converge to identify what Z is, this dynamical exponent. And the first way is just closing of the band gap with system size. So this is a well-known kind of thing, right? Another thing is the scaling of the light cone edge, which I'll determine with bond entropy. And then the last thing, yeah, I didn't have time to show you the math. It's really quite pretty. But do you guys know that for Ising model, you can do Jordan-Wigner mapping and solve it exactly? And so you can imagine if you add terms of the Ising model, as long as you add them in a mean field, you can still do that exact solution modified by mean field. So that's a kind of a standard technique. It goes into SSH model, for example. So I do a mean field solution as well, which means I'm doing Jordan-Wigner with the long range stuff mean field. Did that make any sense out loud? Okay, I'm sorry, I didn't want to put the slide in for time. So, okay, so you're wondering how do we find the phase transition? You know, you can see the gap coming down at the phase transition. This is normalized to this is relative to GC, right? And then you can do a power law fit. I'm sorry for time, I'm just sort of skipping ahead. And then I can do this light cone scaling. And as I mentioned, I'm looking at the bond entropy. And very importantly, wherever the causal, the causal flow of the problem has already arrived, from this initial perturbation, right? That's gonna have very high entropy. Okay. And then where this perturbation hasn't yet gotten to, that will have very low entropy. And so you can easily find a bound. And these three contours, red, green, and blue, are telling us, three ways that you could define where that wall is between high entropy and low entropy. So it's a kind of an entropy front that propagates along the light cone, which I think is kind of cool in these problems. And so from that, we can identify this, and you'll notice that the usual, sorry, I should have clarified, the usual light cone for Ising model is just equals 1. So it's just, it's a perfect triangle, right? And you notice that it's deviating out, right? And that's because, I'm using a lower Q, so it's causing it to deviate out. And if I go to a higher Q, I can cause it to deviate, in actually. And then I get all of these fluctuations around the edge. And those, I think, are due to the frustration of the short range antiferromagnetic piece. And now I sound like one of those condensed matter guys that's just like saying all the critical exponents and ferromagnetic this and antiferromagnetic that. I never understood them when I was a student. So I may have just done the same thing that I was used to driving me crazy. So does that make sense what I'm saying? At very long range, I'm bounded by a power law and it's ferromagnetic, right? But for Q greater than 2 at short range, it flips sign. So if I prefer to have spins anti-line here, and I prefer to have them line up over there, then I have some kind of, communication issue between the two sides, which we could loosely refer to as frustration, right? And I believe that is what's causing all of this business that you're seeing, okay? Did not publish this yet, but I just want to show it to you. I'm very proud of this. So this is the dynamical critical exponent. You'll notice for fraction order of 2, we get back to 1. You see it's following this path for Q less than 2, which looks sort of like a power law. For Q greater than 2, it doesn't be completely crazy. Very non-power law due to the frustration, I believe. Okay, it's our interpretation. And then this is 3 lines of evidence converging. You see the mean field for Q greater than 2 is very bad, but it's very good for less than 2 because the mean field is designed on a power law type of, long range power law type of effect. It doesn't catch all that antiferromagnetic stuff very well. And then this is the wave front expectancy is the red, and the blue is from the band gap. And those are all converging. Okay, I have a ton more in this paper. That could be a whole talk, but I kind of just finishing it. I was writing it up this morning, so I felt like maybe I shouldn't tell you too much about something I don't fully understand, but I feel pretty comfortable with 3 lines of evidence converging. I'm going to go to my conclusions. Does anyone want to ask me a question about this, or kick it around a little bit and think I need to fix something? I mean, I'm really open to any comments you guys might have. I did not even put on the archive yet, so it's my first time presenting.
I will have comments about, technical aspects of the calculation because, long range interactions are notoriously difficult for these kind of methods. And
sure,
on top of that, you're doing time evolution. So you probably need a huge bond dimension.
That's right, and I use a sum over exponential, so I did this for cold molecules. I have a big part of my life, maybe you don't notice, where I worked on long range interactions a lot actually in the past. So the question is whether like this is sufficient for the fractional problem. The long range interaction problem, I think I have been comfortable with. I'm using 10 to 12 exponentials. I really check the conversions of the number of exponentials. Sorry guys, this is technical. That's used to sum up to get the effective long range power law. And then for molecules, I only ever needed like 5 or 6. I think the reason I need 10 to 12 is because it has to also catch the shorter range stuff, short to medium range stuff. Yeah, but I mean, I'm converging it to 10 digits. Yeah, which is maybe excessive. I don't know. I'm a little bit obsessed with good numerics, so.
It's very impressive,
Okay.
my former student worked on a very closely related problem.
Yeah.
And so we should talk after your seminar, but because there are a lot of open questions and maybe your code can help us.
Sure.
And but we can leave that for our private conversation later, so.
Okay, sounds good. Anyone else have any questions about dynamics before I show you conclusions? No? Okay, so, all right. So in conclusion, I introduced fractional calculus, not just into, single particle quantum mechanics, but into quantum many-body problems. And that's really the new thing that we're doing here. In the single particle problem, I told you about tunable tunneling and tunable bound states. So crazily enough, this stuff was solved totally wrong in the literature. The solutions are literally wrong, which, I mean, I don't know how much of my stuff is wrong, so no criticism. I thought last year invented some good ideas, but he got one thing wrong, which is you can't do boundary matching conditions locally. It's a fundamentally non-local solution. So if you match boundaries in a finite well, and you use, same thing out of quantum mechanics books, it's actually incorrect. And so any of the stuff on uniform systems is correct. Any of the stuff on like finite well, whatever, it's actually incorrect. So but I think he's the founder of the area and I admire him very much. Then I told you about a fractional multiscale Ising model. And very importantly, I was able to interpret the fractional order as the Hausdorff dimension, which is dual to the anomalous dimension. And just to remind you, anomalous dimension is kind of the emergent dimension of a critical transition, that doesn't follow your usual units argument. Okay. And then I told you just a little bit about fractional causality. I talked about how Levy flights give rise to modified Lie-Robinson bounds. I quantified that through a dynamical exponent. As a matter of, a practical matter, you get sub or superlinear light cones. And then finally, I actually laid out for you an entire set of open problems, a massive set, right? So this is a path for all many-body physics problems to be solved in the fractional context. Anybody can go do that now. Anybody can go take a soft condensed matter problem out there that involves fractional anything and port it into the hard condensed matter venue or context. For example, you could solve the fractional Fermi-Hubbard. I myself have done work on fractional quantum integrability. I have a couple of published works, including a PRL with Mark Oblowitz on mean field nonlinear PDE, solving for the solitonic solutions of this problem. So there's really quite a lot that can be done. I probably won't write any more papers after this on this field. I'll probably go on to other things I've been discussing with you guys, but I hope this will open up some exciting work for people to play with. So thank you very much for your time. Also, never funded until Ming-Shang. I tried. Yeah, so thanks, Ming-Shang, because it would not have happened without you. I mean, seriously, thank you very much. Questions?
Right, any other questions from the audience? That's similar.
Okay.
Is there anyone online?
Online, let's check.
Oh,
online.
yeah,
Anyone?
let's look. Sorry. Oh, God, that might have been ages ago.
Like, I have to run in my office hours for the final.
All right.
Okay, bye, Greg. Nice chatting with you.
Yeah.
Yeah. I will look into this quantum metric. That's
Okay.
great. Yeah,
Yeah.
thanks. Okay, no, I think.
All right,
Thank
then. So let's thank Nico one more time.
Thank you. Seems like there aren't any questions. It's very hard for me to actually get back to the but
My
there's
computer died, so I made you.
nothing in the
host.
chat. Okay,
So
no,
if
it
no
seems
one's asking
good.
questions- All right,
good.
okay.
I don't know why this thing was freezing. I mean, I actually never had that happen before.
Yeah,
That was weird.
Every week.
Oh, and Andreas was listening. So, okay. Well, thanks, man. So now you know what we've been doing, Yeah.